Okay, it's a few minutes after the hour here, so we just wanted to thank you everyone for joining our seminar series this week. And we're very excited to have Per-Arne Lindqvist here to give a presentation on electric field instrumentation. So I'll just start with an introduction for Per-Arne, but also just wanted to remind everyone that this presentation is being recorded. And as we go through, you can type questions in the chat, and we'll be sure to share those questions with the presenter at the end. And so Per-Arne received his PhD from the Royal Institute of Technology, KTH, and he's a research scientist at the Division of Space and Plasma Physics since 1980, and has been the head of the Division of Space and Plasma Physics from December 2017 to 2019. And he's been involved in electric field instrumentation on many Swedish and international space missions, such as Viking, Freya, Astrid, GEOS, ISI, Cluster, and MMS, of course, with particular focus on measurement quality and data analysis. And on Cluster, launched in 2000, he's the chairman of the WAVE Experiment and Consortium, and responsible also for the Scandinavian Center of the Cluster Science Data System. He's also the Swedish lead co-investigator for the spin plane double probe electric field instrument on NASA's MMS mission, launched in 2015. And his research interests include spacecraft plasma interactions, electric field measurement techniques, reconnection physics, and auroral acceleration processes. And has been the author or co-author of nearly 250 refereed publications and 40 non-refereed papers as well. So with that, we're very thankful, Per-Arne, that you're here. So feel free to take away the screen sharing, and we can start when you're ready.
Okay, thank you very much for that introduction, and thank you for inviting me to give this talk. I will arrange my screen a little bit here. Okay, so today I will talk about electric field instruments, and I will definitely not say everything about electric field instruments, but only a small selection of information, what there is to know. And I will mainly focus on the double probe method of measuring electric fields. There are other methods also, and also focus on instruments and projects where I have been involved myself. So, let's see now, next slide. To start with, I'd like to thank the people who got me started in this field. I would call them my mentors. That's back in the end of the 1970s, early 1980s, namely Ulf Falesson, who was my master's thesis advisor here at KTH, Forrest Moser from the University of California at Berkeley, and Arne Pedersen at ESTEC in Nordvik. They have all been very active in developing the techniques for measuring electric fields with double probes. And at the left, we have a nice old picture with Ulf Falesson and Forrest Moser, and I'm not sure who this is, preparing a balloon experiment. So why do we want to measure electric fields in space? Actually, this is not the topic of my talk, but I'm sure you've heard about it earlier in this series on the magnetosphere. Electric field is very important in space, of course. It can accelerate electric fields. It can help plasma to convect and move around in space. It's essential in the reconnection processes, and also in wave particle interactions. And by the way, I will not say anything about waves and high frequency electric field measurements, but focus more on DC electric field measurements. So this is the outline of my talk. So I will talk about fundamentals of the electric field measurements, comparing double probe method and the electron drift method. As I said, I will focus on the double probes, but I will mention a few slides on the electron drift measurement. An example of very early double probe measurements, and then coming into a little bit of theory also on double probe measurements principle. A few slides on the electron drift instrument, comparisons of the two methods, why and how we want to control the spacecraft with an active control. Some issues with double probe measurements, which are mostly solvable in various ways. How we can use the spacecraft potential as a density measurement. And finally, examples of 4 different spacecraft missions where I'll show a little bit more detail. So how do we measure the electric field? What is the electric field? If we have 2 metal plates separated like this and put a potential difference between them, we will have a uniform electric field between these plates. And obviously it's easy to measure when we have the metal plates. We just connect a multimeter or a voltmeter, measure the voltage difference and divide by the distance, and we will get the electric field. But of course, in space, we don't have this situation. We don't have any metal plates. We have not created the field, but we want to measure a field which is there to start with. And we don't want to measure this. We don't want to disturb this electric field. We want to measure what was there from the start. So we have an electric field in space. We have corresponding potentials in 2 points here, VA and VB. The potential difference divided by the distance will give us the electric field. However, we don't know these potentials, but what we can do is we can insert probes, which we will try to assume these potentials in these points so that VA prime should be as close as possible to VA, and the same for B. And then we can do the same calculation, potential difference divided by distance, to get our electric field. So the challenges here are that we want to make these potentials as close as possible to each other, minimize the difference. And we don't want to modify the field which was there in the first place. So that's what we try to do with this method. So this is the double probe method, where we have 2 probes. So there is another method also if we have a magnetic field in space. If we don't have a magnetic field, we can't do this. But if we have a magnetic field and a uniform electric field, the particles will drift. An electron emitted down here will gyrate around the magnetic field and come back not to the same point, but with a drift step d, because of the Crosby drift. So if we know the magnetic field, the distance here, and the velocity of the particle, we can determine the electric field in space. And this is the electron drift method. So here is a very early electric field measurement, not in the magnetosphere, but in the ionosphere, from a sounding rocket launched by Forrest Moser and his colleague Bruston from Norway. And you see in the schematic diagram on the left here, we have 4 measuring probes, these outer 4 spheres, and the rocket body is symbolized with by the large sphere here. And we measure potential between the spheres by measuring the voltage over these resistors here. So we have these 4 measurements. And the probes are extending perpendicular to the rocket body and at different heights along the rocket body. So we have basically a 3-dimensional measurement here. And data are shown on the right here. And the different curves are by assuming different electric fields parallel to the magnetic field. The magnetic field was essentially close to the rocket body direction. By assuming various parallel potential drops or parallel electric fields, we can get different values for the measured perpendicular electric field. So this was a very early measurement in 1967. However, to do this properly and in the magnetosphere, more theory was developed, and in particular by Ulf Falesson, who was a professor here at the Royal Institute of Technology. He outlined this in a paper in 1967. And basically it's the same thing. We have a central body here and we have 2 measuring probes. Now the slanted line, straight line here, that's the potential or voltage in space before we inserted this measuring system. Now we inserted this, and we will have 3 voltages on these 3 pieces of our system. Probe number 2 here, probe number 1, and the central body. So what we will measure is the voltage difference between these 2 probes on the ends of probably long booms or shorter booms, depending on our project. And we see that the voltage of these probes will not be equal to the undisturbed plasma voltage in that point. And the same with the central body. But this paper discussed various aspects of trying to do this measurement. And the conclusion in the paper was, that reliable probe measurements can easily be done in the ionosphere and the inner magnetosphere, and with larger efforts, probably also in the outer magnetosphere and in the interplanetary space. So this was back in 1967. A little bit more about this theory. How do we actually make the probes assume the plasma potential or as close as possible? So the potential of a body or a probe here, a metallic sphere in space, is determined by the current balance to and from the probes. And I've listed here the 3 most important currents, which are the electrons from the plasma hitting the probe, the photoelectrons being emitted from the probe, and in our case, which we will often see that we use also a bias current, which is sent from the spacecraft or from the rocket body to the probe. So the sum of these currents should be 0. The ion current is often much smaller than the electron current, so I've not drawn that here. And here are some expressions for the electron current and for the photoemission current. And the electron current, this expression actually dates back almost 100 years now from papers by Mott-Smith and Langmuir. And this is why they are called Langmuir probes also, from 1926, where they investigated the current voltage relations for spheres, cylinders, and planar surfaces. And we are here using the equation for a sphere, which is basically a straight line for a positive probe. Now, if we take this equation and plot it, we will have these contributions. So this line here is the photoemission. As the probe becomes more positive, the photoelectrons have harder time to leave the probe, so the net photoemission will decrease. And this is an exponential approximately. The ambient electrons will be attracted more and more to the probe as it becomes more positive. So that's this electron curve. And for a floating probe, the intersection of these two, and by floating I mean that we do not have any bias current, the intersection of these 2 curves will be the probe voltage. We call that the floating voltage. And in a low density plasma, this electron current will be very small. So we will tend to move to the right in this diagram, and the crossing point will give a floating potential which is rather high. So that means that the probe potential is far from the plasma potential, which is not what we wanted. We wanted to be close to the plasma potential. Another disadvantage of being on this part of the curve over here is that if the plasma has small variations in density or temperature or both or electron flux, this curve will be moving a little bit up and down, and the floating potential will be moving a lot up and down because dV di is large over here, large dV di. So what can we do about this? We add our bias current. So we add in our instrument the capability of sending electrons to the probes. So that will add to the ambient plasma electrons and move that curve up here. And now we see that the intersection here is much closer to the plasma potential. So this is the biased voltage of the probe then. And also dVdI is much smaller. So the voltage is insensitive to plasma variations. So that's what we want to do. In a low density plasma, a bias current is needed to compensate for photoemission, to keep the probe near plasma potential and to minimize dVdI. So typically we set the bias current to 1/2 or 2/3 of the maximum photoemission current. So now we know how to work this probe. Of course, to use this to measure electric fields, we always need at least 2 probes. So there are some various ways of doing this, double probe configurations, I call them here. We can have either cylindrical probes like this. They are easier to manufacture, but they don't give such a good measurement in on a spinning spacecraft. So here on the left, we have probes in the spin plane of various spacecraft, and they are generally extended on long, thin wires, which are kept extended by the centrifugal force. Since this is spinning and we have photoemission, the sun is maybe, say the sunlight is coming from above in this picture, it's better to have spherical probes because then the photoemission will be more independent on the spin phase. In the first configuration here, of course, we have maximum photoemission in this phase, and 90 degrees later, we have no photoemission from the probes. These two here, we can only get one component of the electric field component along the boom system. If we want more than that, we need to have more probes. And this is a very typical configuration with 4 probes. There we can get both components of the electric field in the spin plane. And there are variations of this one also. We can have, in this case, all 4 booms are of equal length. In this case, the 4 booms are of different length. In this case, we have even 6 probes, and the booms are of slightly different length. And in this case here, we have more than 1 probe on each extended wire boom. And why do we want more than these? Well, we may be able to see better different scale sizes of the electric field. So these probes here, they are maybe separated by 1 meter, and the probe to the other probe here is maybe the order of 100 meter. So you can see different scale sizes. And I've listed here various spacecraft which have used these different configurations. Now, all of these only give us the electric field in the spin plane, 2 dimensions. If we want a 3rd dimension, the full 3D electric field, we need to add also axial probes. And here we cannot rely on the centrifugal force to keep them extended. So they need to be stiff booms and then probes at the end of the booms. And these probes at the end here could be spherical or cylindrical, with some examples given here for various projects. So MMS, for example, has cylindrical axial probes and 4 spherical probes on equal length booms in the spin plane. So this one just shows the instrument descriptions for the various missions. So now we are measuring. So we will have a, if we take the examples of 2 probes in the spin plane, and this is from the International Sun-Earth Explorer, IC-1, which was launched back in 1977. And here are some of the very first data where we have the magnetic field, interplanetary field, Z component varying, and we have the potential difference between probes 1 and 2. And because the spacecraft is spinning, of course, we get a sine wave, more or less, with variations on top of it. And to get the electric field in space, we need to do a least squares fit to the sine wave and determine the amplitude and phase of this wave. This will give us the amplitude and direction of the electric field in space. Or in other words, we get the sunward and duskward component. And by looking at these data, we can compute from the magnetic and electric field, we can actually compute the solar wind velocity was about 500 kilometers per second. But our data is only at spin resolution, which is often not very high. On IC, it was about 3 seconds. So on MMS, we now have 6 probes, 4 in the spin plane and 2 along the axis. So we have another example here. Now we are in the magnetosheath. We have the top panel shows the magnetic field. The green curve is BZ again, doing a change from positive to negative BZ. And down here we have the 3 components of the electric field in the instrument coordinate system. So the red curve is between probes 1 and 2. The yellow curve is between probes 3 and 4. They're both in the spin plane, so we have a sine wave. And the green curve is between the axial probes. And there, ideally, we should not have any spin variation. And in this case, we see we don't really have very much spin variation. So to get this into a more useful coordinate system, for example, GSE, geocentric solar ecliptic, we despin the data, we use all these, and we get the despun data, the X component, Sunward component, red, the Y component, yellow, and the Z component in green. So here are our despun data, and these are the scientific data then we use for our scientific analysis of processes in space. And the advantage of this is, for one, we have now 6 probes, so we get all 3 components, but we also get a much better time resolution. We can sample these data at whatever sampling rate our instrument is capable of. So on MMS, the nominal sampling rate is 32 samples per second, and in burst data we have more than 8 kilosamples per second. So I promised to say a few words about electron drift instruments also. Some of the projects that I know of which have carried such instruments are the European Space Agency, Spacecraft GEOS 1 and GEOS 2. This was intended to be a geostationary satellite. GEOS 1 was launched in 1977. And it actually didn't reach the intended orbit, but entered a 12-hour elliptical orbit. So they built GEOS 2 from the flight spare of GEOS 1 and launched that, and it came into the right orbit. So it's the same instrument there. We have Freya, a Swedish satellite. We have a Japanese spacecraft called Geotail, which actually carried all of these carried both electron drift instruments and double probe instruments, so that we can compare the 2 measurements, which is very useful, except for Equator S, which was launched and operational like a precursor to the cluster project. The instrument on Equator S was sort of a test trial for the instrument on cluster, made by the same institute. And then finally, MMS, we also have a electron drift instrument. So this is the first one on GEOS, a fairly simple instrument. We have actually 4 of these electron guns which emit electrons out perpendicular to the magnetic field. GEOS was in an equatorial orbit around Earth, where the magnetic field was basically northward, and the spin plane of the spacecraft was also northward. So magnetic field was more or less along the spin axis. So if we emit electrons in the spin plane, they will gyrate around the magnetic field and come back with a drift step, not to the point of origin, but some distance away from that, and are measured by a detector. And we can operate one of these guns at a time, and then measure the signal coming back to the detector as the spacecraft spins. And we can, if we do the maths of all of this, we can see that the detector will see the emitted electron beam twice per spin. And from the timing of where it sees this signal during the spin, we can compute the electric field, both magnitude and direction. So it will give us a measure of the electric field, again, in the spin plane. And this is then also only the perpendicular component of the electric field. Because if there is a parallel field along B, it cannot be measured by this technique. The parallel electric field will just cause the electrons to move away along the field line. And a much more sophisticated instrument is flown on MMS, where we have two of these units where they have combined the gun and the detector into one unit, and they are mounted on opposite sides of the spacecraft like this, and can emit electrons in basically any direction, of course not into the spacecraft, but outwards in a fairly broad emission angle. And also here, by emitting from both of these units at the same time and detecting the signal back at the other units, so the electron beam emitted by gun number 1 is detected by detector number 2 and vice versa. And there we can compute the drift step. And when we have the drift step, we can compute the perpendicular, again, electric field. And this is done by a method of triangulation. There is also another way of doing this, is by looking at the time of flight of the electrons. The electron emitted from this gun here will travel slightly more than 360 degrees. And if it's emitted in this direction, it will travel slightly less than 360 degrees. So they will arrive at different times on the other detector here. And also there we can get the drift step and compute the electric field. By the way, the average of these two times is the gyro period of the electrons. And given the electron energy and velocity, of course, we can then compute the magnitude of the magnetic field. And this is a completely independent method of getting that magnitude. Magnetic fields are usually measured by magnetic field instruments, but here is a way to actually calibrate the measurements of the flux gate magnetometer, for example. Okay, so here is a comparison of the double probe and the electron drift methods. They both have advantages and disadvantages. So the double probe method is conceptually simple. We just measure the potential difference between 2 points in space and divide by the distance. Anybody can understand that. We can have a very high sampling rate. We can measure electric fields which have very rapid variations because we have this high sampling rate. It is independent of the magnetic field. The electron drift measurement needs a magnetic field to make the electrons gyrate. And as a byproduct, we can measure the electron density by looking at the spacecraft potential. I will return to that a little bit later. So these are advantages of the double probe method. Disadvantages are that we have this coupling between the probe and the plasma, which we need to control with our bias current. And sometimes it's difficult to get this good connection between the probe and the plasma, so we actually measure the proper electric field. We are inserting a system of probes into the plasma, which may disturb the ambient electric field that we are trying to measure. It can be sensitive to plasma variations and gradients. If the plasma density increases or decreases, it will affect our current voltage balance of the probes. And to measure the third component with axial booms, we can never make them as long as the spin plane radial booms. Longest axial booms are the order of tens of meters, not hundreds of meters. So the electron drift method has advantages. It's insensitive to this perturbation by the spacecraft. And the reason is, of course, that the electron spends most of its time in duration far away from the spacecraft. The gyro radius can be the order of kilometers for such a electron. It's independent of the spacecraft orientation. And as a byproduct, we can get the magnitude of the magnetic field. However, it needs to have a sufficiently large and stable magnetic field. If the magnetic field is too small, the electrons will travel so far away from the spacecraft that the beam will be very weak when it returns, that it is not detectable. And if we have a varying magnetic field, the beam will also be very hard to detect stably back on the spacecraft. So, for example, in the solar wind with a small magnetic field, which is varying quite a lot, it's not so easy to use this electron drift method. It's mostly used in the inner magnetosphere with higher magnetic fields. The instrument geometry is a bit complicated and the analysis is a bit involved with these triangulation method. We only measure the perpendicular electric field, and we can only use a low sampling rate. I mean, we can never get 8 kilosamples per second. Anyway, the right plots shows here in blue measurements with the electron drift instrument on cluster, and the red curve shows the double probe measurements. And in general, they agree for this case, which they often do. And as you see in this period in the middle where we have rapid fluctuations of the electric field, the electron drift instrument very often does not make any measurement at all. You see there are gaps in the blue curve here. And when it measures the field, it's more like an average of the electric field. It doesn't sense these rapid variations. So I mentioned the spacecraft potential, and now we'll talk a little bit more about that. It's a byproduct, or it's an essential part of measuring the electric field. The electric field is measured by the 2 probes, which we extend away from the spacecraft, divide by the distance, get the electric field. But we also have the central body of the spacecraft, which is actually obeys the same current voltage characteristics. But there we neglect the bias current. We don't send any bias current to the spacecraft. Actually, the bias current from the spacecraft to the probes works a little bit in the opposite direction, but that can be neglected. So the spacecraft will be sitting over here with the floating voltage of the spacecraft somewhere on this right part of this curve, because we don't have any bias current. And if the ambient electron density decreases very much, then the spacecraft will go to very high positive potentials. And this happens sometimes, for example, in the magnetospheric lobes, where the density may be 0.1 per cubic centimeters, for example, we get high spacecraft potentials of tens of volts. This is not a good thing for measuring low energy particles, for example. Low energy ions will never reach the spacecraft, and low energy electrons will be accelerated towards the spacecraft. So the measurements will be disturbed. And sometimes it also disturbs the electric field measurements. I'll come back to that later. So what can we do about this spacecraft potential, which wants to go very high? We introduce a new instrument called ASPOC, Active Spacecraft Potential Control. And this has been flown, for example, on MMS, where we emit, emits 10 kiloelectron volts indium ions, and at a current of about 20 microamps. And we have 2 of these instruments. This is the spacecraft, MMS. So each of these is sitting on the rim here and emitting an ion beam approximately in the radial direction. Now the beam is not very narrow. It has about 40 degrees half angle, so it actually spreads out quite a little bit here. So this can reduce the spacecraft voltage to about 6 volts by emitting these positive charges in the form of indium ions. Here we have a picture of one of the instruments. And to the right, we have simulations showing the potential distribution around the spacecraft in the case of ASPOC off and ASPOC on. And with ASPOC off, in this simulated case, we have a spacecraft potential of about 25 volts. And then that potential extends all the way out on the spin plane radial wire booms. So that's why we have these red lines here. And this is looking now from the side onto the spin plane. We also see the axial booms here have the same potential, 20 to 25 volts. And this really creates a disturbance of the electric field around the spacecraft also. If we switch on ASPOC, the potential of the actual spacecraft will be reduced to maybe like 6 volts or so. Of course, in the beam, in the actual ion beam which is being emitted, we will have a positive space charge. So the potential there will be increased. So there, the maximum voltage there in this simulation is about 12 volts. But the spacecraft itself and the wire booms, they are at about 6 volts. And here is the view from the side. So this is of advantage to being able to measure the low energy ions and electrons. So now I will talk a little bit about various issues and difficulties and problems and how to solve them in measuring with double probes. So one is that we need to have a uniform probe surface to avoid variations during spin. As I said, it's a good idea to have spherical probes on a spinning spacecraft, because then we will have the same photoemission throughout the spin. But of course, if the surface of the probe is non-uniform, then the photoemission will vary anyway. So here are some materials which were tested early in the era of space measurements: aluminum, aquadag, and vitreous carbon. And we can see that vitreous carbon has a very uniform work function. And this work function is what determines the amount and the energy of the photoelectrons emitted. So vitreous carbon was a good idea at the time, and it has been used on many spacecraft. Later, other materials have been used also. So for example, on MMS for the spin plane double probes, the spheres are made out of titanium, and the surface is titanium nitride. The titanium is baked in 800 degrees Celsius in a nitrogen atmosphere to get this surface. And here we have done UV reflectance measurements of these probes. Not a proper work function measurement, but anyway, something which can give an indication of how uniform the surface is. And what we see is that the surface is quite uniform across various parts of the surface. That's shown by the different data series here. There were 16 stripes which were measured. So that was something we did in particular for MMS to avoid variations during spin. It worked fairly well, but not perfectly, as you will see later. Another issue is that we have these photoelectrons, which are of course emitted in the sunward direction from all these parts of the system: central spacecraft body, the probes, various parts of the wire booms that hold the probes. And this will cause the instrument to measure like a spurious sunward electric field. So this probe will be in a more negative ambient potential than the anti-sunward probe here. And that's the same as an electric field from right to left here. So how do we get rid of this problem? One is to introduce various electrical guards and stub voltages to prevent the photoelectrons from moving as they would have moved. This can improve the situation. Another mitigation is to surround or to extend the probe from an extremely thin wire between the boom and the probe here to minimize the photoemission from the surfaces close to the probe. So this picture here shows how it was done on GEOS and IC with various guards and various potentials on these surfaces. It worked partly. And here I show on 4 other different missions how this geometry has been used. So guards and stubs minimize the photoelectronic symmetry. And this has been used on all 4 of these missions. The Swedish Viking, where we have guard and inner tips, which can be controlled at different voltages. On Freya, the same. On Cluster and on MMS, in addition, we took out the preamp away from the probe and put it at a distance of the order of 2 meters with a very, very thin wire in between. And this has drastically improved the measurements on these 2 missions as compared to other missions without this thin wire. So you see the dimensions here, it's a fraction of a millimeter, this thin wire. So this is what needs to be done to improve the quality of this double probe electric field measurement. Another issue is that when we insert these long wires into the ambient plasma, where we had an electric field to start with, we will actually short circuit the ambient electric field. So here is from a simulation where we see the top is in the spin plane, and the bottom we see from the axial direction looking down on the spin plane, how the spacecraft and the wire booms affect the potential distribution around it. And what this boils down to, in effect, is that when we measure the probe-to-probe potential difference and divide by the distance between them, we measure an electric field which is only a fraction, or well, actually a large fraction, but not 100% of the ambient field. It's the order of 80 or 90%. We also affect the probe to spacecraft potential voltage by having this long wire boom here. So that is also reduced by about 20%. So this has been studied by simulation and analysis, and it's not really much we can do about it in building the instrument, but the effects can be corrected for during data analysis. And that is done, of course, before data are published. So we come back to this spacecraft potential again. I remind you that high plasma density, we can have a low spacecraft potential, but for a low ambient plasma density, we can drive the spacecraft potential very high. And this can actually be a disadvantage and an advantage. So a disadvantage is when we have cold ions moving like this. For a spacecraft with a low potential, we get a very narrow wake, but for a spacecraft with a high spacecraft potential, it will repel these ions. And we get a very large wake here behind the spacecraft. This can then be handled by switching ASPOC on, and we will lower the potential of the spacecraft to decrease the wake again. And on the right, we see 2 examples from cluster 1, where ASPOC was not operational, and cluster 3, where ASPOC is operational. And we see that at the point when ASPOC is switched on, the cluster 3 instrument measures the correct electric field, whereas the cluster 1 instrument, which does not have ASPOC on, you see the red curve measures very large negative values here, -6 millivolts per meter, which is an erroneous measurement. We can compare it to the blue curve with EDI. So here ASPOC can help us to get rid of this wake effect. The side effect is actually that the double probe measurements can be used in this way to determine the cold ion outflow, and that has been done and published in the literature. The spacecraft potential, high spacecraft potential, low density, and vice versa. So spacecraft potential can be used to measure the electron density if we calibrate it. And here we have a few calibration curves for various years on cluster. And here on the right, we have an example of comparing these. The red curve is the electron density as determined from the spacecraft potential. And the green is a resonance instrument, and the black is a particle instrument with low time resolution. And this can be used when we cross boundaries with a high timer, with a fast response, where we can then use the spacecraft potential as a proxy for the density and do timing analysis of boundary crossings. Here we have 2 magnetopause crossings. So finally, a few examples from some spacecraft where we have been involved in Sweden. I list here a number of spacecraft where we have had hardware involvement. We were PIs on 5 of them, and the ones in blue here I will show some more data from. So we start with cluster. I wanted to show you the how this boom unit looks. So this is manufactured in Berkeley under Forest Motors Group. And in the left part here, we have the actual probe. The circular part here is a drum containing the approximately 40-meter long wire boom. The circular part here is an electric motor to drive the deployment, and the rest of the box contains electronics and mechanical gears and stuff. So when deploying, we open this door and the probes comes out, and then you can have a controlled deployment of the wire boom. So 16 of these are flying, 4 on each of the 4 cluster spacecraft. And after 20 years in space, almost half of them are still operational. The rest have become unoperational, probably due to micrometeorite impacts. The Astrid 2 was a small satellite developed in Sweden and launched from Russia, where we had a little bit odd deployment. The wire boom was wound up on the circumference of the spacecraft, 2 turns, and then there was a conveyor belt here to control the deployment of these booms. So this is a little bit unorthodox way of deploying the wire booms on Astrid 2. And then MMS, which is of course the latest and the best in all of these, where we had the spin plane double probe led by us at KTH, and the axial probe led by LASP in Colorado. And you can see location of 1 STP unit here on the spacecraft and the 1 ADP unit here on the bottom. A picture of the STP unit on the left here. And here we have been in space for about 6 years now, and 2 probes have failed due to micrometeorite impacts. And here we are fairly certain that they are actually impacts, because they have been measured also by the accelerometers on board. So here are some details of the MMS instrument. We have the schematic of the unit up here, which is a collaboration between many different institutes. The actual deployer here was mainly the work of University of New Hampshire. The boom electronics boards at the back here comes from Sweden. The probes were manufactured in Finland. The preamplifier comes from LASP. And here you see the preamplifier, and the preamplifier housing doubles as a guard also to prevent the photoelectrons. We have the outer guard and inner guard. And to the left, you see the details of the configuration in the stowed position. Probe hemispheres were made from titanium and nitrided. Inside the probe, there is a yo-yo to deploy this thin wire between the probe and the preamplifier. And at the bottom right, we have a schematic diagram to show how we drive these different guard voltages and the bias current also. So the wire connecting the deployer to the preamplifier has actually 7 strands inside it. And this is the ADP boom, which is the order of 12 meters long. And at the end of the boom, there is a cylindrical receiving element, which is the actual probe. And also there we have stub and guard arrangements. And the signals from all of these 6 probes, V1, 2, 3, 4 in the spin plane, 5 and 6 are axial, are fed into a digital signal processor and sent down to telemetry. The DSP is also from LASP. For MMS, we need to keep track of the bias current because it actually needs to be changed sometimes, since the photoemission of the probes changes with time. So there we do these kind of bias current sweeps to determine the best operational point on this current voltage curve and set bias currents individually to each probe, according to a table here as an example for MMS3. It turns out that in spite of the efforts to make a uniform probe surface, the probe surface is not perfectly uniform, but the photoemission from the probe actually does vary with the spin phase. Most of this variation comes from the fact that we have the wire near the probe, but some of it comes actually from non-uniformities of the probes. And each probe has an individual photo emission, so they are not equal. But this can be then compensated for with the bias current and also operation in software. And finally, just to show an example of this is the instrument built here at KTH, launched in 2018 to arrive at Mercury in 2025. So here we have this schematic of the boom deployer, where the cable is wound up around between 2 concentric cylinders. We have the probe here in red, we have the preamplifier in yellow, we have the boom electronics in the back, and these are the 2 flight units. A particular problem with BepiColombo is that it will be very close to the sun, so it will be very hot. So we needed to put mirrors on the door of the deployer, and also the surface of the preamplifier is also mirrors to reflect the sunlight. The probe here is made of titanium aluminum nitride, to keep it not too hot. But it's a challenge to go to Mercury. Here we see the magnetospheric orbiter where we have our probes, and the other spacecraft here is the planetary orbiter, which has instruments to study the Mercury surface. So we'll see how this works out in about 4 or 5 years from now when we deploy it. And that's the end of my presentation. Thank you very much.
Excellent. Thank you so much, Per-Arne. It was a very interesting talk and lots of great content here. We have a few questions already in the chat. And actually, I just wanted to mention for anybody who might be signing off or has to go soon that next week, of course, we'll return again on May 3rd, where Emma Bland is going to be discussing the SuperDARN, or the Super Dual Auroral Radar Network. So feel free to tune in next week for that. And without further ado, let me return to the questions here. We do have a few from the chat. So Kyle mentioned from slide 13, he was wondering, when you fit the electric field, is that done on board or on the ground? So we can maybe go back to that slide to see.
Yeah. Okay, so the fitting of the spin fit to these data, that is down on the ground. So these data are sent down to the ground. On IC, this was the order of 8 or 10 samples per second. So these data were sent down to the ground, and then the spin fit was done on the ground in software. We actually do the same kind of spin fits on MMS data to determine offsets and gains that we need to determine to get good quality measurements. But then when we do the D-spin, we use the full resolution. But D-spin in both these cases is done on the ground.
Okay, excellent. And so, yeah, then I posted a question here too. I had done a little bit of work with the EDI instrument at UNH, and I was just curious, you mentioned for the electron drift near around maybe slide 16 or so, that you mentioned these various techniques for how the instrument would work to catch these gyrating electrons. And I'm just wondering if the time of flight technique is needed to, say, distinguish between returning electrons that have undergone multiple gyrations, say, instead of just one gyration, maybe they've gone 2 or 3 times. And so I don't know if one technique is better than another for distinguishing those.
Well, I'm not an expert in this electron drift instrument, but I would think that it's not necessary to rely on the time of flight to determine whether there are multiple gyrations. Multiple gyrations, for each gyration, the beam would get weaker and weaker. So the strongest signal is, of course, the measured one after the first gyration. And as I understand it, also they have a coding of the intensity of the beam, so that when they detect it later on, they compare that with the coding of the emitted beam to determine, so they get the right beam back, so to say.
Sure. Okay.
I'm not really an expert here, so I couldn't answer definitely.
Sure. Yeah, that sounds familiar. Actually, I remember them mentioning that coding, so they can actually catch it. It's a very fascinating way that the instrument works. All right, so moving on to the next question. So Todd Anderson was wondering from slide 23, is the short circuiting of the ambient field, or can it be accounted for by carefully measuring the instrument boom impedance and estimating the leakage current before launch, or is there a procedure for accounting for the short circuiting after the launch?
I think this short circuiting cannot be determined or measured before launch. This is something which needs to be done in orbit to calibrate the instrument by comparing to various other techniques. For example, comparing double probe and electron drift technique, but also comparing to plasma moments, velocity, cross magnetic field. V cross B will give you the electric field, but it can also be studied by doing simulations like this to determine what fraction of the shorting of the electric field is to be shorted. But you cannot measure it, do measurements on the ground to determine it.
Mm-hmm. Okay, great, thank you. And our final question for now, it looks like Elizaveta was asking, what do you think about checking the frozen-in condition validity using the electric and magnetic field MMS observations? So maybe just general comments and your thoughts about that issue.
Well, I guess that's actually the main scientific question for MMS to study in space is reconnection, which is in a process ongoing in the magnetopause and in the geomagnetic tail and in other places. And of course, in those regions, the frozen-in condition actually is no longer valid because the magnetic field goes to zero. It vanishes in certain places. And there we can then measure the electric field to see how the particles or they measure the electric field, which will affect the particle motion and accelerate the particles. But otherwise, if we are not in these, as we call diffusion regions, electron diffusion region, ion diffusion regions, then the frozen-in condition is a good approximation. And then we can, of course, that's when we can calibrate the electric field measurements by using V cross B, which we cannot do in places where the frozen-in condition is not valid. So it's complicated, everything goes together.
Exactly, the heart of the diffusion region has much complexity to be probed. So, okay. Excellent. Well, I think that concludes our questions and also brings us to the top of the hour here. So again, we just want to thank you wholeheartedly, Per-Arne, for this presentation. And we'll be sure to have this posted as soon as we can on our YouTube site for anybody who wants to review. And it'll be very helpful as a reference to just review many of these instruments on from several of the missions that you discussed in your talk. So thank you again.
Thank you very much. And thanks for listening and thanks for hosting this meeting.
Certainly. All right. Well, thanks everyone and hope to see you next week. Okay.